Okay, let's look at buffer solutions in more detail. All right, so a buffer solution, it's a solution of known pH which resists changes in pH on additions of small amounts of acid and alkali. A buffer solution usually consists of a weak acid and one of its salts in solution, or a weak base and one of its salts. And the classic example is that. We've seen that before. So you have ethanoic acid and it sets up that equilibrium in aqueous solution. Brilliant. Now remember, this is mainly on this side. There are many, many more molecules of ethanoic acid than there are of ethanoate ions and oxonium ions. When we dissolve the salt in that same solution, so we've just basically added to water, it ionizes fully. So all of these particles, ions, are dissolved and they become aqueous. Okay, so there'll be a small concentration of this, a large concentration of these ions from the salt, and that's going to be important. So for a buffer solution to resist changes in pH, then we've got to kind of try and keep the concentration of the hydrogen ions constant, or as close to constant as possible. So let's consider the two possibilities. Imagine that we've got this buffer solution and it's contaminated by an acid. So whenever you've got a question on buffer solutions, always write out the equations. There's always going to be two. The equation which is an equilibrium to do with the weak acid, and the equation which shows that the salt fully ionizes. And that reminds you that we've got lots of that and lots of that. Okay? So if we add some hydrogen ions to this, accidentally we contaminate it with an acid, then the hydrogen ions will react with the large pool of ethanoate ions and produce ethanoic acid. So the hydrogen ions are used up and the pH is not significantly affected. We can contaminate it with an alkali, of course, and we've got to see how that can be controlled by the buffer solution. So there are a couple of ways of looking at this, but if we contaminate this with an alkali, then we can say, well, what's the alkali going to react with? Well, it reacts with potentially the oxonium ions. That uses up the hydroxide ions, but then this equilibrium will shift to the right in order to restore the hydrogen ion concentration. Okay, that should say a weak acid, and it gives H2O. Thus the pH is not affected, or it's not affected significantly. We could also think of this as the hydroxide ions reacting directly with the ethanoic acid to produce ethanoate ions, and what would they produce? Ethanoate ions and water. So we've used up the hydroxide ions with the ethanoic acid. The pH is not affected or affected very little. Okay, there are two possible ways of describing what happens in order for the pH not to change significantly. We need to have a general case because they could throw any weak acid at you. So you'd always write down the equation for the dissociation of the weak acid, and you'd always write down the equation for the dissociation of the salt. Okay? So in this solution, if we add an acid accidentally, then it reacts with the ethanoate ions, or it reacts with the salt ions, which we've got lots of from the NaA, to produce the weak acid again, thus soaking up the accidental contamination with these hydrogen ions. Okay, so remember, just make that clear. We've got lots of these A- ions, and they would soak up the added hydrogen ions. If we accidentally add an alkali, then they react with the H3O plus from the weak acid to produce water, and then this equilibrium shifts in order to restore the hydrogen ion concentration and keep the pH more or less constant. Okay, how do we calculate the pH of a buffer solution? Well, we've got Ka for any weak acid. Now there's the Ka for ethanoic acid, isn't it? So how are we going to use this? Well, in this case, these two terms in the numerator are not equal. Why aren't they equal? Well, they're equal because we've added sodium ethanoate. So they're not equal because we've added sodium ethanoate. So this term now is much bigger than this term because lots of ethanoate ions came from the salt. Okay? So we have to assume a couple of things for this to work. We have to assume that the concentration of the ethanoate ions is just from the added salt. We don't get any ethanoate ions from the dissociation of the acid because it's considered to be so small that it's insignificant. Okay? And the second assumption is, as the concentration of the ethanoate ions is high, then the dissociation of the acid will be very far to the left. So the concentration of the acid is considered to be the original concentration of the acid that we add. The concentration of the acid does not change. Okay? Now all of this is a little bit abstract until we start to do questions. Now there's a little note here, which is something that's again a bit abstract, but you'll see it as we come through this. That the ratio of the acid concentration and the ions, the ethanoate ions in this case, it's actually a conjugate base, isn't it? It's from the weak acid. The ratio of these two things must stay more or less constant so that pH remains more or less constant. Now that comes from this expression. Look, pH is dependent on the concentration of the hydrogen ions. Ka is a constant. So the ratio of these two must stay more or less the same so that this term stays more or less the same. Okay? Little changes in these numbers won't matter because they're big concentrations. So small changes in big concentrations don't have a big effect. But that ratio is key. You'll see this when we do some questions. So let's do an example. We prepare a solution of 0.1 mole per decimeter cubed ethanoic acid with 0.3 moles per decimeter cubed sodium ethanoate. Those two are mixed together. Okay? Calculate the pH of a solution. And you've got the Ka for ethanoic acid. So we always write down this expression. Remember, in this case, these two terms are not equal. So what do we put in here? Well, the concentration of the ethanoate ion is the concentration of the salt. Why? Because the salt was fully dissociated. So there you go, it's 0.3 moles per decimeter cubed sodium ethanoate. The concentration of the acid is the original concentration of the acid, 0.2. We assume that it's not dissociated. That's one of the assumptions, isn't it? Put those numbers in and we get something that looks like that. Great. Rearrange that and we get the concentration of hydrogen ions to be that. It's going to be this multiplied by this divided by this, isn't it? If we've got the concentration of hydrogen ions, then it's just a couple of steps to work out the pH. pH is 4.946. No units because logarithms don't have units. They eliminate the units. Okay, so this is how we work out the pH of a buffer solution if we're given the concentrations of the acid and the salt. Now, we can do a little academic test here and we can say, what would happen if we added 1 centimeter cubed of 0.1 molar HCl to 999 centimeter cubed of this buffer solution? Okay, so we've got a buffer solution that's got a pH of about 4.9. let's think about what happens if we add acid to this particular buffer solution. How many moles of acid have we added? All of these questions you can freeze and you can try them, and then you can look at the answer that I give. So look at these figures here. How many moles of acid have we added? Now we've got to assume that it's completely dissociated. So it's going to be the concentration times the volume. The volume has to be in decimeter cubed. We've got a number of moles of acid. And that acid is going to react with these ethanoate ions. Okay? The acid is going to react with the ethanoate ions to produce ethanoic acid and water. Why? Because this is strong acid, this is a weak acid, and these ions are going to soak up this acid. So they react with the ethanoate ions. So in that case, if those ethanoate ions are reacting, then their concentration will decrease. By how much? Well, by that much, the same amount. Okay, so if they've reacted with the oxonium ions, their concentration has decreased by that much. They've made ethanoic acid. So the ethanoic acid concentration has increased. By how much? By the same amount. Okay? This is what the buffer solution's done. It's reacted with the oxonium ions. It's soaked them up. If we substitute these figures into the expression we had before, that's the expression for Ka. Remember, this has gone down slightly, this has gone up slightly. So let's have a look at the numbers. Same expression, but 0.3 minus the 1 times 10 to the minus 4, 0.2 plus the 1 times 10 to the minus 4. We can take the number of moles to be concentration because we're working in 1 decimeter cubed. Rearrange that, we get the hydrogen ion concentration, and we can work out the pH, and the pH is 4.945. Well, that's pretty impressive, isn't it? Because the pH has gone down only by 0.001 of a unit. We added a tiny amount of acid and the pH went down a very small amount. Okay, you might think, well, that was just a tiny amount of acid. Literally 1 centimeter cubed of 0.1 molar HCl. Yeah, okay, it was only a small amount of acid. But let's consider what would happen if we added the same volume of acid to 0.999 decimeter cubed, so 999 centimeter cubed of distilled water. How many moles of acid? Same as before. And now that is in 1 decimeter cubed. We've dissolved it in water, haven't we? 999 centimeter cubed. So what's the concentration of the oxonium ions? The concentration is that many moles per decimeter cubed. Great. What's the pH? The pH is 4. The pH is 4. The pH has dropped from 7 to 4. It dropped 3 units on the pH scale. 3 units. Whereas before, our pH dropped by 0.001 with the buffer solution. I think that's pretty conclusive, isn't it? Pretty impressive as well. Okay, the pH of blood. Ugh. This is not something I'm particularly fond of, but something to think about. Okay, your blood is a buffer solution, and it has to deal with lots of acids and alkalis that the body produces. Mainly acids. The body likes acid more than it likes alkali. Having said that, the blood is slightly alkaline. I think it's got a pH of about 7.5, which it needs because it needs to absorb all the acids that it produces, like lactic acid when you do exercise, etc. I'm not going to pretend to be a biologist. So we have to set up a buffer solution. Carbonic acid is our main molecule here because obviously carbon dioxide dissolved in water gives carbonic acid. It's a weak acid, great, which is why acid rain exists, but it's always been very weak until we came along. and it has this equilibrium with this, they call it a bicarbonate ion in this text. I've changed it to a hydrogen carbonate, but these two are synonymous. Bicarbonate, hydrogen carbonate, synonymous. So this is the equilibrium that's set up. Okay, we've got carbonic acid molecules and we've got hydrogen carbonate molecules simultaneously. So we have obviously a buffer solution. Now, this is biological, but due to complex reactions under normal circumstances, you've got many more, 20 to 1, more hydrogen carbonate ions than you have carbonic acid molecules. Now, that doesn't make sense to a chemist, because a chemist would say, well, this is a weak acid, so the equilibrium is going to be heavily to this side. But apparently not. Apparently, due to reaction with, what was the thing it reacts with? I think it reacts with your red blood cells, some kind of enzyme that causes this reaction to be further to the right than we would usually expect. Don't worry about that. The important thing is, for a buffer solution to exist, they have to be present simultaneously. The hydrogen carbonate molecules, the carbonic acid, and the hydrogen carbonate ions. Okay, so there we go. We've just mentioned that there's more of the hydrogen carbonate ions than we'd expect, essentially because the body produces more acids, so we're going to have to deal with those acids. Now, carbonic acid is not stable in aqueous solutions, so when it does exist in any higher concentrations, it decomposes to form carbon dioxide and water, and the respiratory system, your lungs, gets rid of the carbon dioxide. Okay, so we're going to combine these reactions, and we've got these kind of simultaneous equilibria taking place. Okay, this is the one that we saw on the previous slide, and this is the one that shows how carbonic acid decomposes to give carbon dioxide and water. That, for me, if you could learn that phrase, that deals with everything you need to know about this section. The production of carbon dioxide from this reaction couples to the carbonic acid bicarbonate buffer to the respiratory system. So this basically couples this reaction to the respiratory system. Now, think about what happens to the above equilibria when the acidity of blood increases. So something happens in your body, you do some exercise, and your body produces lactic acid. So it increases the concentration of the oxonium ions. That swings that equilibrium to the center, producing more carbonic acid, and more carbonic acid would swing that equilibrium to the left, producing more carbon dioxide, which you can get rid of through the lungs. So your body has this process of getting rid of the acids it produces through carbon dioxide expelled through your mouth, your nose. Okay, isn't that amazing? What a fantastic system, no? And it has to get rid of the acidity of the blood. We really don't want acidic blood. We want slightly alkaline blood, apparently. So there you go. That's what you have to learn. Like I say, that's the key. This is the key set of equations. And as soon as you start saying things like, what happens if acids produce, then your chemistry kicks in and you know it shifts all the way to the left. Read the pages and answer the questions.